Today we'll be talking about divergence theorem. So, the very last thing I learned in Calculus 3 was divergence theorem. So, this is a big milestone for all of you, and also this will wrap up my Calculus 3 playlist in this channel. So, divergence theorem. And out of all the theorems, I would definitely say that this one is probably the easiest to remember and the easiest to do because it's just one dot product. It's just one dot product, and it's quite simple. So what does divergence theorem state? Well, when you first learned surface integrals, you had your vector field dotted with some normal vector of some, I guess, little s. I'll just write little. Big S or little s, doesn't matter, of some region. And this is your, I guess, surface integral. But you can calculate the flux. So calculate the flux of this surface integral using a triple integral of over some volume. And it goes like this. It is just a dot product between your vector field and the del. and this right here calculates flux. So Stokes' theorem calculates circulation for a surface integral, and divergence theorem calculates flux. But the thing about divergence theorem is that you need a closed surface. You can't have something that's open at the bottom, like a hemisphere. You need like a box or like a full sphere or any blob that's just completely enclosed. That's one of the conditions for the divergence theorem. And just like all the other theorems, you need some counterclockwise orientation, continuous partials, simply connected, whatever all that is. But let's get into some problems, and I'll show you how easy this actually is. We have a unit sphere as our region, or I guess volume. That's probably the more proper word. We have a unit sphere for our volume that we're going to be integrating over. So that gives us a pretty big indication that we have to use spherical coordinates. And we also have this guy right here. So you're going to see different notations for different problems throughout your Calculus 3 career. Sometimes you see dot dr, dot dn, and maybe you have your vector field dot dn. It's just or like you have vector field dot n ds. It's just a whole lot of annoying notation, but they all mean the same thing. So for this one, we have a surface integral. You're given your vector field here per the standard model or the standard definition of a surface integral, and you're dotting it with dn, which means that you're finding some flux. So if you dot anything with some normal vector, you're finding flux. And we have a closed region here, a unit sphere. So that just gives us a very strong indication that you should be using divergence theorem in this case. So when you're calculating flux and you have some closed region like a unit sphere. So how do we turn this into this guy right here on the right side that makes the divergence theorem also easy? Well, let's dot our del with our vector field. So we have to find the x partial of the first component, the y partial of the second component, and the z partial of the third component. Very easy, just power rule the rest of the entire thing. And why am I writing it like this? You're supposed to add it all together because it's a dot product. Let's add them all together. So 3x squared, 3y squared, plus 3c squared. This is our dot product with the del and the vector field here. Now you don't have to worry about any normal vector. You don't have to find a normal vector because all you have to do is do a triple integral over your region. So what's your region? Well, your region is just the unit sphere. So rho is from 0. Let's write right below the unit sphere. Rho is from 0 to 1. Phi is from 0 to pi, and theta is from 0 to 2 pi. So these are the bounds for a unit sphere. And if you don't know what this stands for, I have a video. It's called Intro to Unit Spheres. No, not Intro to Unit Spheres. Oh my god, I was reading this, intro to spherical coordinates. So that might help you understand what this stands for. But let's write down our integrands. Our integrand is the dot product, which we calculate up here, and we are integrating over some volume, dv. Now let's turn this into spherical coordinates. Well, here's the thing about this. You can factor out the 3 to get x squared plus y squared plus z squared. And then this is an identity. This right here is equal to rho squared in spherical coordinates. Just like how x squared plus y squared is equal to r squared in polar coordinates, x squared plus y squared plus z squared is equal to rho squared. So we can actually substitute this for rho squared. So we have 3 rho squared here. This entire thing is equal to this. And if we rewrite our triple integral, we can factor out the 3. So let's move this forward. We can factor out the 3, and you get rho dv. But the thing about dv in spherical coordinates is we have to take into account a Jacobian. So we have rho squared sine of phi dp d phi d theta. It doesn't matter which order you integrate. Our Jacobian is the rho squared sine of phi. So if we multiply that by rho squared, we get rho to the power of 4 sine of phi of dp d phi and d theta. Again, we factor out the 3 here. That's why there's a 3 out here. And we should just set the bounds in accordance to whatever order we integrate. So rho is 0 to 1, phi is 0 to pi, and then theta is 0 to 2 pi. So all we have to do is solve for a triple integral. So if we want to solve for this triple integral, maybe I'll write it up here. I want to solve for this triple integral. I'll just start off with I'll start off with rho. So the integral of rho is rho to the power of 4 sine of phi is just rho to the power of 5 sine of phi from 0 to 1. So this is just 1/5 sine of phi. Then we integrate with respect to phi. So we have 1/5. Let's actually factor out the 1/5. Let's save the 3 here. Let's factor out the 1/5. Let's save the 1/5. And then multiply by our end answer. So we have sine of phi d of phi. And this is just equal to negative cosine of phi from 0 to pi. And this is just equal to 1 plus 1, which is 2. And then once we have 2, all we do is integrate 2 with respect to theta, which is just equal to 4 pi. But don't forget, we need to multiply 4 pi by all the values that we saved. So we have 1/5 times 3, and this is all equal to 12 pi over 5. So 12 pi over 5, using divergence theorem, is our answer for this surface integral. In this problem, you are given a vector field, and you're already given your region. So that's pretty easy. Most of the time in exams, in your math, calculus 3 exams, you will get some region already defined pretty easily in rectangular coordinates, or in, again, spherical coordinates, unit sphere, or they can give you some cylinder to test your cylindrical coordinates, cylinder of like height 5 or something like that. For this one, you're given a simple cube from 0, 1, 0, 1, 0, 1, all sine lengths of 1. First thing we're going to do, let's dot product this vector field. Let's dot product this. So if we dot product this, we get 4x plus 10y plus 1. So we're just finding the x partial of the first component, the y partial of the second component, and the z partial of the third component, and adding them all up per the dot product. And then all we have to do is write our triple integral. So our triple integral bounds from 0 to 1. We don't need to do any coordinate transformations, so we can leave these in rectangular coordinates. And we can integrate this from dx, dy, and dz. Doesn't matter, you can write dz, dy, or dx. Order of integration does not matter. And then let's just solve this integral. So we have 0, 1 for 4x, 10y plus 1 with respect to x. So we're integrating this with respect to x first. Let's move this up. We're integrating this with respect to x first. And this integral with respect to x is 2x squared plus 10y x plus x from 0 to 1. And if we just plug in all of this, we get 3 plus 10y. Now we integrate with respect to y. So we have 3 plus 10y dy is equal to 3y plus 5y squared from 0 to 1. And this just equals 8. And if you integrate 8 with respect to z, you just get z, 8z from 0 to 1, which is just still equal to 8. So 8 is our answer here. And all we had to do was just, well, we had the region already, but all we had to do was just find the dot product. That's probably the hardest part of the divergence theorem. And after that, it's just a triple integral that hopefully all of you guys are familiar with by now. So as always, if you have any questions, put it down in the comment section.